start like a new topic, which is going to be the final like sort of module of the course, which is going to be computational interactability. And in particular, we'll be talking about this class of problems called NP. Okay, so what we have done till now we have looked at like various methods and to design efficient algorithms, right? And what has been our working definition of efficiency? It's polynomial time. So an algorithm is efficient if it is polynomial time algorithm, right? And we have seen many problems which can be solved in polynomial time, using different approaches. But the question can be asked, like, like, are there some problem which cannot be solved in, let's say, in efficiently, right? That is in polynomial time. And then another question can be that can we prove that they cannot be solved? Okay. And the answer to this question is not that straightforward, that okay, here is a problem, or these problems are there and we show that they cannot be solved in polynomial time, because showing lower bounds is extremely hard. Because what does it mean to say that a problem cannot be solved in certain time? You have to give an argument against every possible algorithm, that no matter how cleverly one thinks, no matter what way one approaches the problem, one cannot get certain running time, an efficient running time, right? So, and the answer to this question is like, so even though, so for this, we actually know that, there are some problems. The answer is yes. But, I mean, those problems are not very interesting. Are quite artificial. On the other hand, there are a lot of problems which are very natural, like coming from real world, or even like mathematical problems, combinatorial problems, and so on. But we don't know any efficient algorithms. On the other hand, we also can't show. I mean, not we can't show, we don't know. We have not shown that, or we have not proved that they cannot have efficient algorithms. And whenever I'm using the word efficient, what I mean is polynomial time, right? So this is a very strange situation that we are in. That okay, these problems are there. We don't know how to solve them efficiently. We cannot show that we cannot solve them efficiently. Nobody knows how to like uh, get a polynomial time running time bound for these problems for some algorithm. So what to do? Right? And one way to look at this situation can be that okay, we can look at the problems which are sort of related. Can we give some ordering, right, among the problems? So many different problems in this set are related to each other. So again, this is like a very rough outline of what we are going to see. And then we will flesh out the details that, okay, what do we mean by these problems? What do we mean by they are related to each other and so on. But this is just to give you like a bird's eye view of what is going to happen. Okay. So many different problems in the set are related to each other. And how are they related? So what is this relation? That if one can be solved, in polynomial time, or let's say efficiently, or let's be more precise. Then all of them can be solved in polynomial time. So you can find a set of such problems, right? And these problems are called NP-complete problems. Okay. And there are thousands of these. Right? And again, we are saying that if one can be solved in polynomial time, all can be solved in polynomial time, but we still don't know if any one of them can be solved in polynomial time. Right? So this is the situation. But since we are saying that if one can be solved in polynomial time, then all of them can be solved in polynomial time. So does a polynomial time algorithm exist? If we ask this question is going to have the answer, like the same answer for all the problems in this set, for all the NP-complete problems. So either all the NP-complete problems don't have a polynomial time algorithm, or all of them have a polynomial time algorithm. Okay. So, I mean, what is the idea of NP-complete? That these problems are hard for all practical purpose. Right? So if you come across a problem and you find it out that this problem is NP-complete, then probably you should stop looking for efficient algorithm for that problem. Again, polynomial time. Because if that problem has a polynomial time algorithm, then all these bunch of problems have polynomial time algorithm, and none of which has been found. People have been looking for years for any one of these problems to have polynomial time algorithm, and they have not found. So it's less likely that you will find a polynomial time. But if you do, then you win $1 million. So if you can design a polynomial time algorithm for any of these NP-complete problems, you get $1 million. So that's the prize announced by someone, or like some institution, Clay Institute. Okay. So that is how hard the problem is. So unless you want to wager like your time and effort to win like $1 million for a long time, so you can do that. But generally the thing is that okay, maybe you should be looking for something simpler to solve, to build up the solution, rather than looking for the solution directly, or looking for an efficient algorithm directly for the NP hard problem. So any questions about this picture? No? Okay, good. So let's now, start fleshing out some details of what we mean by these relatedness and so on, right?
That the problems, so
Yeah.
the problems in NP complete set, aren't they means there is no proof that they can't be solved in polynomial time, or we are
Yes,
still
that's
looking for that proof?
say what is the second option you're saying?
So means is it that means we are unable to even show that they can't be solved in polynomial time, and we are unable to find that also, or they can't be solved in polynomial time? It has been proved.
No, it has not been proved, and that is what so any answer. So okay, so I'm saying that even getting the efficient algorithm will get you $1 million, but if you also show, if you can prove that the NP complete problems cannot be solved in polynomial time, then also you win $1 million. So we don't know any of it, and of course, one way or the other, it has to go, right? That either it is uh, and this, like succinctly is called P versus NP problem, and we'll see what why. So P is the class of problems that have polynomial time algorithms, and NP is the class of problems which we'll define later. But generally, for now, as I said, just imagine them to be some class where they don't have efficient algorithms. So yeah, I hope that answers your question, Rishabh.
Yes, sir.
Okay, good. Good. So the thing that we are going to, or how are we going to relate these problems, is going to be this thing called reductions. Okay. So by using reduction, we will compare the difficulty or we'll use the word complexity of solving different problems. So how can we compare, right? That one problem is more or less difficult than the other. So there's one very natural way of doing it, that if you can solve one problem using the other, then we can say that the first problem is not very hard. It can be solved using the second problem, right? So for example, we had solved bipartite matching using max flow min cut, right? So we can say that bipartite matching is actually not harder than max flow min cut, because we can solve it using max flow min cut, right? So let's formalize that definition or that intuition. So what does the formal definition say? And now we are going to also okay. So another thing is that what do we mean by using this problem? We can solve this problem. It will take some time to even reduce the problem. That okay, what is going to be the new instance of the problem that we are going to use to solve the original problem? So all that should be efficient as well. It's not that okay, I'm using something to solve this problem, but then I'm taking exponential time here itself. Then there is no use of using the black box, so to say. Okay, so let's look at the definition, and that might make things clearer. So we say that a problem Y okay, and we denote it by less than or equal to P. And what does we say that Y is polynomial time reducible to S? X. Right? If any arbitrary instance of Y can be solved using a polynomial number of standard computational steps, plus a polynomial number of calls to a black box that solves X. Okay, so what does that mean? That we have this algorithm A for Y. And what does this algorithm do? It takes polynomial time by itself. But it can also call a black box which solves X in one step, right? Or just like, the black box just gives you the answer. So that's what like. And it can make polynomial number of queries to the black box. Okay. So this is what the setting is. And if that happens, then we say that Y reduces to polynomial time reduces to X.
Sir,
Yeah.
sir, this does not necessarily imply that Y will have a smaller running time than X.
No, not necessarily. Smaller running time than X. I mean, not smaller essentially. So we are doing polynomial time here, but it will imply something. So can somebody guess?
Sir, here, what is the size of input for the queries? Is that also polynomial?
Exactly. So that's a good question. So when we say that this polynomial number of steps, this counts writing the question, the query, for black box. So since we have to write every bit of the input that we are going to send to the black box, where that will count in the number of steps of, so that cannot be more than polynomial, the input size to the black box. Okay, so we'll come to this that, okay, if y reduces to x, then what is going to be the relationship between running times of y and x? Okay, so just hold your thought for now and we'll get to that. So there is some relationship. It's not necessarily that, okay, one is going to be bigger, because here we are hiding a lot of things in this P, right? That inside the P, we don't really care that what is, more or what is less and so on. We are just saying that it takes polynomial time. So inside polynomial time, weird things can happen, but we are not going to go for that. This machinery is generally defined to deal with hard problems for which we don't know that polynomial time algorithms exist or yeah. So, and for those problems, now the implications will start coming. That if y reduces to x, then what does it mean? Okay, so that is what we are going to see now. So let's say that, all right, we reduce to x. So how much extra power does the black box give? How strong is the black box, right? And this very intuitively should depend on the complexity of x. Like if x is something trivial anyway, or x is very easy problem, then why do I need to use a black box anyway? I can solve the problem by myself. Algorithm A can solve the problem by itself. And if the black box is really powerful, that means that x is a very hard problem and the black box is just breaking that problem and giving you the answer immediately, right? So this depends on the complexity of x, how much extra power we are getting. So let's look at one particular case when, so if y reduces to x, polynomial time reduces to x, and x can be solved in polynomial time. Then what can we say? Like x can be solved in polynomial time by itself. Then the extra power is not that much. Why? What can we do? Or can somebody guess the implication? If x can be solved in polynomial time, then can we say something about y?
Then y can also be solved in polynomial time
Yeah, why?
because we are making polynomial number of calls to x and additional polynomial steps to convert it to x.
Exactly. So why? So the claim is that, or let's call it a lemma. Says that suppose y polynomial time reduces to x, then if x can be solved in polynomial time, then y can be solved in polynomial time. So as Amit was saying that the proof is actually just one line. So what are we going to do to solve y in polynomial time? We just, instead of this black box, we replace this with some algorithm for x. and embed that algorithm inside A. Right? So whenever A makes a call, query to black box, run the algorithm B for X, right? For solving X. And this takes polynomial time. Polynomial time in what? Input of X, which is again polynomial. Because the number of steps of A is polynomial. Right? So this, one call takes polynomial number of steps, and then there are polynomial number of such calls. So overall running time of A or this new algorithm is polynomial. Right? So what did we do? We just embedded this this black box inside A, because this black box was not doing anything much anyway. So it is just solving the problem X, and which can be solved in polynomial time. So instead of the black box, now we replace this with the polynomial time algorithm B, which solves X. Okay. So is the lemma clear? Any question about
the converse of that? Like if y can be solved in polynomial time, then x.
No, right? So y reduces to X. So the thing is that you can always reduce a easier problem to a harder problem. Generally, I mean, so now you are doing some easy problem and you are reducing it to something very hard. That does not give you much. So maybe the easy problem can be solved very easily, but just because you are using a very huge black box, which is not really needed. So actually the time to solve X might be much larger than the time to solve Y.
Okay, so you are saying that y can be solved by some other method.
Exactly. So whenever we talk about the running time of solving some problem, we talk about the whether it can be solved efficiently at all, like running time of the best algorithm possible, and so on. So whenever I'm saying that all this can be solved, that means there exists an algorithm which can solve this in polynomial time. And here, since I have to show that there exists an algorithm that can solve Y in polynomial time, I show the existence of such an algorithm by showing an algorithm explicitly. Any other question about this lemma? So actually, we have seen these things, somehow in action before, but not exactly like this. But again, let's look at the example of bipartite matching and max flow. So we can say that bipartite matching reduces to max flow, right? Because what did we do from bipartite matching? We took this bipartite graph, then we made an instance of max flow, and we answered something depending on what the output of max flow was. And this can be solved in polynomial time. So bipartite matching can be solved in polynomial time. But now we actually want to look at the other direction. So what is the contrapositive of this lemma? Anyone? Just tell me the contrapositive.
If y cannot be solved in polynomial time, then x also cannot be solved in polynomial time.
Exactly. So we have shown that lemma. This is just the contrapositive of that, but this is what we'll be using a lot. So, or this is what the intuition is about. So suppose y reduces to x in polynomial time. Now, if y cannot be solved in polynomial time, then x cannot be solved in polynomial. So this way somehow, now the idea can be to spread the hardness from y to x. So if we know that y is hard somehow, then we can now spread the hardness. If now we can show that y reduces to some problem x, then we know that x is also hard and so on. But then again, the caveat that we don't know really that y is hard. But this helps us in building a relative ordering of problems. Okay. So any question about this contrapositive of the earlier lemma? Okay, so if not, let's look at some reductions now. Just to give you an idea of, I've been talking about x and y till now. So first, let's say independent set and vertex cover. Okay. So let's first define quickly what are these. So given G is equal to V comma E, S subset of V is an independent set, and we can call it IS, or let's call the problem IS later. Independent set in G if G induced on S is edgeless. Graph. And what do we mean by G induced on S? This is the graph G prime is equal to S comma S cross S intersection V. So basically we want to take only the edges, because basically we want to take the subgraph which is just induced on the vertices S, and we want to take edges which have both endpoints in S. Right? Let's call it GS only by call. Okay. So what is an independent set? That you have a graph and you have a set of vertices. So suppose we have, okay, should have drawn. So suppose you have hexagon, then what is an independent set? This is an independent set. Because there is no edge between any two vertices of that. Good. Now let's look at what is the vertex cover. I think, have I defined? Maybe not. Have you seen vertex cover? Defined it earlier in the course somewhere? Can somebody say if we have, otherwise we have not. Is the vertex cover of G if GS or not GS? If for all UV in E, we have UV intersection S is not equal to empty set. Right. So what does this mean? This means that for every edge in the graph, at least one of its endpoints has to be in the vertex cover in the set. Okay. So again, if we look at this, then what is a vertex cover? A vertex cover can be, again, the same guys are vertex cover also in this case. Or if you have just like, let's take a different graph. Okay, suppose you have this, and you have this, and you have something else, let's say. Right. And you want to find a vertex cover. What can be a vertex cover, a possible vertex cover? So let's say, let's include this guy and this guy. This is a vertex cover. No, sorry. We need to include one more. While now you look at any edge in the graph, this edge, it has one endpoint in the vertex cover. This edge has both. This edge has one. This edge has one. So on. I don't know whether it is the minimum vertex cover for this graph. I think it should be. Yeah, I think it should be. Anyway. So this is a vertex cover. But as I was talking about the minimum vertex cover and what is the trivial independent set in a graph? And what is the trivial vertex cover of a graph?
Only one vertex is independent.
Only one vertex. Yeah, that is going to be independent because of course there are no edges. And what is the trivial vertex cover?
All vertices.
All vertices. Right. So vertex cover is generally so yeah, now let's define the problems. We have defined this, but we are going to define the problems in decision version. I'll come to what that means. So vertex cover. Let's define the problem. So input is G is equal to V comma E and an integer K. And question is, does G have a vertex cover of size less than equal to K? Right. Similarly, we define independent set, or let's abbreviate VC for vertex cover, the problem. For independent set, again, the input is going to be the same. G is equal to V comma E, K in N. And question is, does G have an independent set of size at least K? Right. So here we are. So these questions are like what we call decision questions or decision problems. Answer is yes or no. And while the optimization problems, we want to find the maximum size vertex cover or maximum size or minimum size vertex cover or maximum size independent set. So maximum or minimum size independent set or vertex cover, right? But we are going for decision versions. So we'll be dealing with decision versions only in this part of the course. And that does not make the problem very hard or easy. So can someone say which one is actually easier? Or can we solve like, one using the other?
The maximum or minimum could be reduced to the decision one.
Actually, the other way is easier, right? Decision can be reduced to maximum minimum very easily. Just find the maximum minimum and see whether it is k or not. So both can be reduced to each other. So for optimization to decision, it will take, let's say, log n steps if we want to reduce optimization to decision. Because now we need to decide for like, you ask for n over 2, then you make a binary search sort of. But decision to optimization reduction is very easy. That is one step. One step. You just ask the optimization version, get the answer, and then see whether whatever you got is greater than k or not, and so on. So these are related. So this was just to say that, okay, we'll be just dealing with the decision problems in this part of the course. And they don't make much of a difference in size of the, like, in complexity of a problem. Good. So now for both these problems, vertex cover and independent set, don't know if there exists a polynomial time algorithm. But we know something that let G is equal to V comma E. S is an independent set in G if and only if V minus S is a vertex cover in G. Right? So these problems are very intimately related. And I'll just draw a picture for the proof. So forward direction, S is an independent set in G. So you have this S, which is an independent set. You look at V minus S. Then S cannot have any edge. So all the edges are going to be here or here. That means for every edge, one of the endpoint is going to be in V minus S. Right? For every edge, one endpoint has to be in V minus S. If not, both endpoints are going to be in S, and then S is not an independent set. Similarly, for the other direction, again, the picture remains the same. That V minus S is the vertex cover. That means for every edge, one of the endpoints is in V minus S. So the other side has to be independent set, because if not, then it contains one edge, and that one edge is not possible because V minus S is a vertex cover. So any question about this proof? This is like, very simple, just like, just looking at the graph and what it means for something to be an independent set and what it means for something to be a vertex cover. So any question about this? if not, then now we get something that another lemma which says that independent set reduces to vertex cover. And how will we do this?
Sir, find out independent set and then simply do uh, v minus
No,
s.
we have to solve independent set using vertex cover. We want to reduce independent set to vertex cover, so we cannot find the independent set.
Okay, sir. So we'll find vertex cover and then do v minus vertex cover.
Exactly. So, but we are looking at the decision version of the problem. So suppose G comma K be an instance of independent set, right? So what are we going to do? So let's say that G is equal to V comma E, where mod V is equal to N, suppose, then solve G comma N minus K for vertex cover, give the same answer. Why? Because now G has a vertex cover of size N minus K. G has a vertex cover of size N minus K if and only if G has an independent set of size K. Vertex cover of size, yeah. So you can show this. Okay. So this way you can reduce independent set to vertex cover. What about, so even the other way around, like, is very, it's the same. Vertex cover, again, independent set. And again, the proof will be exactly the same. I'm not going to do it. Right. So this way now you got these two problems are, and now you know that if independent set can be solved in polynomial time, then vertex cover can be solved in polynomial time. Or if vertex cover can be solved in polynomial time, then independent set can be solved in polynomial time. So like one can be solved in polynomial time if and only if the other can be solved in polynomial time, right? So similarly, there are these other problems, like one is called set cover, which is sort of a generalization of vertex cover. So what is the input? Input is a universe U, which has n elements, and let's say some m sets, S1 to Sm, which are subset of U, and you are given a k as integer. And the question is, can you find k sets? So let's say Si1, Si2, Sik, such that union of all these is equal to U, the universe. Okay, so one is union and one is the so what are we asking here? That we are given some set family and we are asking whether k of them can be combined to get the universe U, right? And what you can show is that, so this is like a covering problem. You want to cover the universe using certain things, and set cover, vertex cover also is a sort of covering problem. And you can show that vertex cover. So I would like you to think about it before you actually look for the proof in the book. This is a very simple reduction. And similarly, there is this thing called set packing, where the input is, again, input is going to be the same, 1 to n, just like a graph. So a graph is, you can say that all the sets have size 2 or something, or in some sense, or all the sets, depends on how you are going to make the sets, but this is a generalization to sets of graph. And then S1 to Sm are a subset of U. And then again, you are given k belonging to n. And question is, does there exist again SI1, SI2, SIK such that they are mutually disjoint? So what do you want to do? You want to pack the set as tightly as possible, but still, like, you want these sets to be disjoint. So can you pack the K of these sets which don't have anything in common inside U? That is the question. And then there is a lemma which says that independent set reduces to set packing. And this reduction is very similar to the previous reduction, vertex cover to set cover. So since these are more general problems, we can reduce the, the easier versions of problem or the special cases of these problems to the general version of problems. And I would like you to think about these two results before you look them up in the book. This is like very simple, and you should be thinking about it a bit to get to the answer or to see that why these things happen. Okay, so this is all I wanted to do today, and tomorrow we'll see some more problems, and maybe if we can, then we'll get to NP and what are those things. So right now I just wanted to do some reductions, just following the book. Any questions for these problems or for the vertex cover and independent set reduction?
Sir, actually I had a query regarding the assignment 3. So should I ask it here or?
You can ask it in Piazza. I'm responding there.
Yeah, sure. And sir, can you actually share the average of minor examination with us? It's
Average
not available.
minor. Okay, yeah. I'll send it.
Okay, thank you so much.
Any other questions?
Sir, is this the last assignment, or will there be more assignments in the course?
This is the last assignment. Any other question?
Excuse me, sir.
Hi, Udita. I have got your email. I'll reply.
Okay, sir.
Anything else about the what I taught? No. Okay, then thank you for coming, and I'll see you guys tomorrow.